my name is Jim Holcomb with Evolve Security, and I'm here with Isaiah Sarju. And we had a lot of questions about our last video about the Meltdown and Spectre vulnerabilities. So I thought it'd be fun to get Isaiah back in here and ask him some questions personally. So Isaiah, can you go ahead and introduce yourself before we get started?
Sure. Thanks, Jim. I'm Isaiah Sarju, Senior Security Consultant with Evolve Security. Yeah, you might remember me from the Spectre and Meltdown video that I did a little while back.
Awesome. So the first question that we actually had was about this idea of side channels and covert channels and how they differ and how they're actually used together. So can you jump in and explain what is a side channel, what is a covert channel, and how they actually apply to these particular vulnerabilities?
Yeah, I think it's good that we kind of provide some background on some of the terms that are used throughout the white paper and are necessary to define what's going on with these specific, very technical vulnerabilities. So side channel and covert channels are a great place to start. A side channel, in a sense, is something that discloses information about something that shouldn't otherwise be known. The example I used, I believe, in the last video was, let's say you have a neighbor's house and you can't actually see people in the rooms, but whenever somebody's in a room, they turn on the light and you can see the light from the outside. Being able to see that light from the outside is acting as a side channel and disclosing information that should be kept sensitive of where people are throughout the house. Or kept secret, excuse me. And so that's an example in the real world. Example that we've seen from a technical aspect, our researchers have proven that they can look at the lights on a hard drive and be able to tell what it's reading and writing and reproduce that information. And so on the technical side, that's a good example.
So with that said, can you tell me about covert channels?
Oh yeah, I forgot to mention that. So covert channel is similar to a side channel. A covert channel is anything that's used to exfiltrate data secretly. So we've seen this from a technical side with embedding information in, let's say, SSL certificates and sending those certificates outbound to a remote host and using that as a conduit to exfiltrate information. And so that's a covert channel. It's any channel that's being used to exfiltrate data that shouldn't be exfiltrated from that environment. Why we see both of these terms arise in these white papers is because there are known side channel attacks against CPU cache memory, which I assume we'll get into. And because there are known attacks and the ability to read that memory, then people can use, or attackers can use that CPU cache as a covert channel to move data from one area of memory to another area where it shouldn't be moved to. So then the CPU cache, because there are side channel attacks known on it, can be used as a covert channel.
So it becomes a covert channel.
It becomes a covert channel when you combine it with side channel attacks to learn information.
So before we actually talk about the vulnerabilities, can you discuss some of the CPU architecture that sort of makes these vulnerabilities possible, a little bit more in detail, like pipelining and all of that?
Yeah, so before I do that, I'll talk about virtual memory and how that's used. So we have this idea of user space memory and kernel space memory. User space memory, that's where all of our regular processes are. And then kernel space memory is that memory that's reserved for the kernel, that's located, that's loaded at boot time. And that is dealing with the mediation between software and hardware. And so it's very sensitive information that needs to be protected, and it's sensitive system operations. And so within the CPU, when it's processing, either kernel space memory or user space memory, there's what's called page tables. So there's a kernel page table and a user space page table. And that's maintaining the memory mappings from the maintained virtual memory and the actual physical memory. And so a CPU maintains these tables and virtual memory, that is, so they have all these ranges of user space memory that are then mapped to actual physical memory. But that's a smaller subset than the entire physical memory. Then with the kernel space mappings and the kernel page table, how it has historically been done with modern processors is the kernel space virtual memory maps to the entire physical memory. And so if you're able to read kernel space memory, you're able to read any memory because there is user space memory that is contained within that kernel space.
Because of the way it's mapped from the virtual memory.
Exactly.
There's that overlap.
Yep, in the kernel page table. Because the kernel page table maintains a mapping to user space memory along with the rest of physical memory.
Okay. And what about some of those more difficult to understand concepts about CPU architecture? Pipelining,
Yep.
out of order execution, all these words that are be thrown around. Can you sort of jump into those and explain what they actually are and why they make these vulnerabilities possible?
Yeah, so let's start with pipelining. It's a great place to start. So modern CPUs pipeline instructions, and this is an architecture decision to keep CPUs as busy as possible. It increases the efficiency of the CPU. So CPU's goal is to stay as busy as possible, so while it's fetching memory from one area of memory, maybe pulling from a physical read instead of from a cache, which is faster, it's actually having to go do a physical read on the memory. It's going to move ahead with instructions. And so we get this idea of out of order execution. So you'll have one instruction that's being executed by other parts of the CPU, but the next instruction can be handled by other parts of the CPU and it'll start to do that. And so we have what's called speculative execution and then transient execution. So speculative execution is the CPU making the best guess at what logic to perform next. And it might get this wrong. And when it gets it wrong, those instructions are considered transient execution because they don't actually affect the program flow. The results are thrown out. But here's the key thing for these vulnerabilities is it changes the microarchitecture of the CPU cache. And so then that CPU cache can be used, can be attacked using side channel attacks, which we'll get to.
Okay, so speculative execution comes from that idea of pipelining, where they're trying to perform as many operations as possible.
Yes.
And then it's going to try to guess. So for some instances, it's going to try to guess what it should execute.
Exactly. So especially when there's, we'll talk about this especially with Spectre, how when there's potential different paths, it's going to perform the path that it thinks is correct.
Most likely. Okay. And then those executions become transient when they're supposed to be thrown out, or when they are thrown out by the CPU, but they may still be written to cache.
Yeah. So they affect the microarchitecture, and what we care about is it's affecting the CPU cache.
Very cool. So Spectre and Meltdown, they're technically two different types of vulnerabilities, and there's a few CVEs associated with them. I think Spectre is 2017 5753 and 2017 5715, and then there is Meltdown, which is actually CVE 2017 5754. So Spectre actually has two vulnerabilities associated with it, and Meltdown. So can you sort of explain at a high level why maybe two vulnerabilities may be classified under Spectre and then this other vulnerability is Meltdown and how they're separate, just at a high level?
Absolutely. So Spectre deals with user space processes attacking the memory of other user space processes. Meltdown deals with user space processes attacking kernel memory. And so these user space processes are any program that's running, like your browser, that runs in user space memory. Your document processor, such as Word or a thin client web application running your browser, that's all running in user space memory. And so an attacker can get their code into user space memory by executing JavaScript. So that's where everything on your system is really running. That's the things that we care about, we see, and we interact with.
Okay, so it's really that difference between user space to user space and then user space to kernel.
Exactly, yeah.
So would you say that maybe the Meltdown vulnerability is more critical than the Spectre vulnerabilities, or how would you classify them in terms of which one is more dangerous, or even which one's easier to exploit?
Okay, so it's hard to answer that question because they're doing separate things. The idea of being able to read kernel space memory is especially critical. Because if you can read kernel space memory in the current configuration of kernel page tables, you can read all of physical memory. So you not only get user space memory, which is contained within that kernel page table, but you also get the entire kernel space memory, which is the entire physical memory. So at first blush, something like Meltdown is really scary, but when we talk about mitigation, it's actually the opposite way because of how long we're going to be dealing with the vulnerabilities.
So we've talked about at a high level the difference between Meltdown and Spectre, but then again Spectre is sort of divided into these two variants.
Yes.
Can you explain what the difference between the two variants are?
Yes. So there's conditional branch misprediction exploitation and indirect branching exploitation. Okay. So conditional branch misprediction comes from, again, a modern CPU architecture choice, and that CPUs learn to make the best decision. So when CPUs are running, they're looking at conditionals. So conditionals are like if statements, and this can be, for our use case, we'll talk about it being true as the most common conditional path.
If something is true, do something.
Yeah.
Else, do another thing.
Exactly, or else don't do anything. Yeah. So with Spectre, with conditional branch misprediction, the malicious program trains the CPU to take a true path. And so it trains it with if statements that are always going to true. And then it has an if statement that actually is going to evaluate to false. But because of out of order execution, the CPU says, while I'm waiting for the responses, is this true or false, I'm going to perform the true statement because I'm predicting it's going to be true. The rest of this program has already evaluated it true. So I'm going to expect that it's actually going to be a true answer. And so then within that true clause of execution, it does something it shouldn't. It goes and reads the memory of another user space process. But then it fails. It fails to do that because it actually evaluates to false. And so there's no exception thrown for accessing memory it shouldn't, because in the end, the program never actually tried to do that when the correct execution path is followed. But it affects the CPU microarchitecture and it affects the CPU cache. And then side channel CPU attacks can be used against the CPU cache, and that's really outside the scope of these papers. But they are documented, and there are defined ways of performing those attacks to gain that information out of the CPU cache.
So it seems like both these vulnerabilities just deal with once getting data that they're not supposed to get to the cache, and then getting the data from the cache with the covert channel. That is sort of an already documented process. So that's not really what these vulnerabilities are called.
Yeah, it's not novel information. What's novel about these vulnerabilities is the precision at which you can go retrieve this information, the accuracy of attacking specific pages of memory. And so that's how it's done with conditional branch misprediction. There's also indirect branching. So indirect branching is when the program has to jump to somewhere else, whether it's jumping to another function in its own process memory, or it's jumping to, let's say, a system library. These can be ambiguous jumps, but again, the malicious program can train the CPU to make specific jumps, especially when it's ambiguous, when it's rating for is it a direct branch, is it a direct jump to a memory address, is it a jump to a register's address, is it a jump to the memory address that's held within a register. When that's ambiguous, it will depend on its training, how it's been trained to make the best guess of where it's jumping. And if the malicious program can train it to jump to a known area of memory for known processing, that then will affect the microarchitecture in a predictable way with sensitive memory data. And so it's very similar to return-oriented programming gadgets that we've seen in the past with other exploitation along those lines of using these small gadgets to produce the desired outcome, and the desired outcome is a change to the CPU cache with sensitive information.
So it seems like one deals with branch prediction, those conditional if-else statements. The other deals with training the CPU to jump to certain other spaces in memory that are
to perform desired execution.
So I imagine, is it difficult to train the CPU to speculatively make these executions, like to train it to always follow the true path? Or train it to go to a certain space?
It's not difficult, and they've shown this in the proof of concepts that because you can just iterate. If you understand the target that you're attacking, and that's a good point that you bring up. Spectre is actually very dependent on the target of the software, while Meltdown, which we'll talk about, cares more about the type of CPU. That's why Meltdown affects mainly Intel processors, while Spectre is affecting a whole suite of processors because Spectre is focused on that software-specific environment that it's going after. But once you understand that environment, you understand how to train the CPU in that environment.
So it seems like there may be a lot of work to exploit this. You might have to put in some work to understand what you're attacking.
Yes.
But it is dependable in the sense that once you understand how to train it to either follow a certain branch or jump to a certain space of memory, it then becomes relatively easy.
I wouldn't say easy, but it's well documented.
Yeah.
And it becomes possible, yeah, absolutely. And then it also is dependent on the systems not being patched. So hopefully we talk about remediation too. Did anybody have a question about that?
Yeah, we've had a few people ask about what they can do. They want to get their systems patched, which we'll talk about in a bit.
Great.
So we've touched on Spectre in depth, but let's talk about like Meltdown. Can you dive into how the vulnerability actually works, especially given what we talked about earlier with virtual memory and physical memory?
Absolutely. So Meltdown is being used to attack kernel space memory. And so this happens because kernel memory is supposed to be isolated. And it is using a vulnerability in the Intel CPU architecture that allows the CPU to fetch data from memory that is in the kernel page table, and have that affect the CPU cache. And so how you exploit a system using Meltdown is the program purposefully tries to retrieve information from a kernel memory space. But this would cause a memory access violation, similar to a program trying to read from another program's memory space. But with this specifically trying to read from kernel memory space, it causes a memory access violation. And so what the malicious program does is it catches that exception so that the program doesn't crash. But when speculative execution is performed, that memory is retrieved and it affects the CPU cache. So although the exception is caught and the malicious program doesn't immediately get access to that data, it can then perform documented side channel attacks against the CPU cache to retrieve that information that has then been written into the CPU cache.
Okay. So when you try to access something in kernel memory, you're stopped. You get an exception thrown, meaning there's an error that you have to catch and then handle.
Yes.
However, the CPU will still execute the instructions that was supposed to occur after that?
It will still it still tries to retrieve that memory, especially so when it's happening out of order execution. It's going to go retrieve that memory and it's preparing for the program. When it's performing speculative execution on behalf of a user space process, it doesn't mandate the memory protections that should be in place. So that's the Intel vulnerability, that the CPU will go retrieve information from kernel space memory when it's not supposed to, while performing speculative execution. Now, these speculative commands become transient instructions because they get discarded when that error occurs. The CPU says, okay, there's an access violation. I'm not returning this data to that process that asked for it. But while retrieving that data that it shouldn't have done it in the first place, it's affecting the CPU cache, and so that can be attacked later by the malicious program with a side channel attack.
So what a lot of people are asking is, what can be done to actually mitigate these vulnerabilities, from within the operating system or, at the CPU level? How do you actually stop these vulnerabilities from being exploited?
Yeah, so we'll start with Meltdown because that's the simplest to solve. What needs to be implemented are patches. Unsurprisingly, patch your system. But specifically, how these patches are working, they're using what's called kernel page table isolation, or KPTI. This is the evolution of a patch that was actually released back in June of 2017 called the Kaiser patch. I forget the exact acronym for that. It's a pretty long one, but it has to do with kernel page table isolation to efficiently prevent side channel attacks, something like that.
Is that like an extra layer of, because virtual memory uses page tables?
Yes.
Is that like an extra layer for a little bit more protection?
What it actually is it's isolating the kernel page table and separating that from the making that inaccessible to user processes when performing user space process execution. So previously, what could happen is, while performing user space processing, a user space process could ask to go retrieve information from a kernel page address. And because the kernel page table was available to that user space process, it shouldn't be. And with KPTI, it isolates that. And so now when user space memory is being processed, the kernel page table is not even available to it. So the CPU can't even go look up that data and then affect a change to the CPU cache.
Okay.
So that's why it's called kernel page table isolation.
Makes sense. And then can you discuss what's being done with the Spectre vulnerability?
Yeah, so Spectre is much harder to remediate. That's one of the reasons why they named it Spectre, is because they say it's going to haunt us for a little bit. And so some of the initial thoughts on doing this are halting sensitive speculative execution and flushing branch prediction models when switching between contexts. So real quick, what that means is when there is speculative execution that may be trying to access other areas of memory that it shouldn't, that the CPU doesn't actually follow that speculative execution. And so in the end, this actually slows down computation efficiency because it's no longer doing speculative execution. The other one is flushing branch prediction models when switching between contexts. And that means that the training that the CPU is doing is not remembered when moving between contexts.
So you brainwash it, or you undo the brainwashing.
Exactly, so that the brainwashing, if you will, that occurs by the malicious program doesn't affect other programs when they're executing, and then allow the malicious program to gain information via side channel attacks that it shouldn't have access to.
So you're no longer able to, do that initial training that could then allow you to.
You can train it, but only for your own process.
Only for your own process.
Yes,
okay.
And that also slows down efficiency of the processor. So it really comes down to patch your systems.
Yeah.
There have been patches put out by Microsoft and Apple, and those are mainly for the KPTI implementations. Linux, like for Meltdown. Like I said, with Linux, the Kaiser patch has been around, so just making sure that your specific Linux distribution is using the most up-to-date and patched kernel.
I think it's 4.14. It was backported to 4.14, and then there were extra measures put in place for 4.15.
That sounds right. I'd have to check on it to make sure. And so, but with Spectre, it's going to take some time. So we've seen some level of patching, but it's not consistent across every single operating system and every single architecture. So 64-bit versus 32-bit architecture. So we're going to be dealing with this for a little bit.
So patch your system, make sure it's up to date.
And then finally, perform defense in depth. This is a great example of why we need defense in depth. Because an attacker has to be locally on your system, that means you need to keep your software up to date themselves. Make sure your browsers are up to date. There have been patches in browsers to help mitigate these vulnerabilities with the JavaScript interpreters. And so making sure that not just your operating systems, but also the software running on them are up to date. And then protecting your perimeter, making it more difficult for that malicious code to get loaded onto a system, either via web browsing or potentially, from a USB getting inserted or from someone getting phished.
Sounds like a good plan. Well, Zaya, thank you so much for talking with me today. I learned a lot, and I hope you all at home did too. And stay tuned. We'll be covering more popular vulnerabilities as they're discovered, and what you can do to stay safe at home.
Thanks, Joe. It was a lot of fun.